So there are certain commercial and manufacturing issues with respect to fuel cells. Let us see what are they and how they look like. So we have Carnot cycle, which can be used to compare fuel cells with internal combustion engine motors as generators of energy. So before commercializing any fuel cell, we need to compare the corresponding Carnot cycle internal combustion engines. So when the performance is better, then only we can go for fuel cells. So this theoretical cycle imposes limits on the performance and construction of any energy transformation unit by high pressures and temperatures according to the upper efficiency limit. It means this theoretical cycle will be imposing some limits on high pressures as well as temperatures with respect to the efficiency limit. And also the dimensions of the heated machine also influence the overall efficiency directly, hopefully by about 30%. Okay, the overall efficiency will be impacted by the dimensions of the heated machine. And in the same way, theoretical limitations exist for fuel cells, although they may not be as narrow. So whatever is this cycle here mentioned, that is of Carnot cycle, that means it is of internal combustion engine. So it is not for fuel cell. Similarly, these dimensions of the heated machine are also for internal combustion engine, right? So let us combine all these, otherwise it will be confusing. So when these limits are all there for Carnot cycle, of course there will be in a same way theoretical limitations exist for fuel cells. So all those things should be known before going for commercializing it. And the more pure the oxygen and hydrogen used, the higher the overall fuel cell efficiency rates, which are around 70%. So if you use pure forms of oxygen and hydrogen, you will get high efficiency as that of 70%. And such rates would be justified only in an aerospace mission or in oceans or similar environments where the costs of hydrogen and oxygen are not as relevant as in ordinary power plants. So that means we can only go for the pure hydrogen and oxygen for aerospace applications and even in oceans or similar environment kind of things, where it doesn't matter the cost of hydrogen and oxygen, because they are at most important, and the fuel cell application is most suited for space shuttles and aerospace as we discussed. So there, since the costs are doesn't matter, we can go for pure forms of hydrogen and oxygen usage, right? And of course there are investments mainly in three areas, like the development of a 5 kilowatt reformer to be integrated with a fuel cell stack tolerant to fuel reforming. And tolerance to fuel reforming processes allows for greater fuel flexibility, simplifies system design, and can enhance system efficiency and performance, making it a desirable feature for integrating reformers with fuel cell stacks. Right, we should have tolerance to fuel reforming processes for better performance and flexibility of the fuel cell system. And also commercially available fuel cells that operate with pure hydrogen and are integrated with electric vehicles. In this particular aspect of developing electric vehicles, the manufacturing investment is mainly concentrated. Also for diffusion and training in the manufacturing, production and use of fuel cells. This is also very important. We should have training in the manufacturing process and production as well as use of fuel cells. So the commercial and manufacturing investment has been concentrated mainly in these three areas now, right? That's it.